right, let's go over the Unit 6 learning targets 1 through 4 as a review to get ready for the upcoming assessment. So first, it says define these terms. So let's do solvent. Solvent is the substance in the greatest amount. Typically, water is the solvent that is most common, versus the solute is the substance dissolved in the solvent. Example, salt. A solution is a mixture of two or more substances that is uniform throughout. So by definition, all solutions are homogeneous. A mixture in which substances are distributed uniformly. Example, the ocean is a homogeneous solution for the most part. I mean, if you're talking about like an area of the ocean where there's a bunch of fish mixed in, well, then that would be heterogeneous. So, but usually you're talking about a mixture that is not uniform throughout, such as chunky salsa. You might take one bite of the salsa and get a lot of jalapeno, and you might take another bite and not so much. A word that I associate with dilute is weak. Not much solute dissolved in a solvent versus concentrated, strong. Lots of solute dissolved in a solvent. So you can see those words were not very specific, not much and lots. So molarity is a measure of concentration, the number of moles per liters of solvent. Okay, you dissolve some salt in water. What's the solute, what's the solution, and what's the solvent? Salt is the solute, water is the solvent, the dissolved salt water is the solution. I'll just say the salt water is the solution. Okay, circle the correct answer. If you mix some rocks with water, will it form a homogeneous or a heterogeneous mixture? That's definitely heterogeneous. It wouldn't be the same throughout. Like sugar water would be the same throughout. Same with another ionic compound. This is like a salt, so that would be homogeneous. But oil and water would be different throughout because the oil would stay on the top. Okay. Next, what is concentration? Concentration is how much solute is dissolved in a solvent. We use molarity as the unit most common for measuring concentration. Molarity is the number of moles dissolved per liter of solvent. Sketch a picture of a dilute solution and a concentrated solution. I'm not trying to break my stylus here. Describe the difference between them. The concentrated solution has more solute particles dissolved per liter than the dilute solution does. Okay, moving on to the next learning target. That first one, just to reiterate, was that you could distinguish between these terms. What is the molarity of a solution if you dissolve 5 moles of solute into 10 liters of solvent? So here's molarity. So you can take moles divided by a liter. So 5 moles divided by 10 liters. 5 divided by 10 is 0.5 molar. Next, it says you need 500 milliliters of a 0.1 molar solution of hydrochloric acid. You have solid HCl powder as well as a stock solution of 12 molar HCl. How would you make this solution using the solid HCl powder? Well, first, I would calculate how many moles of HCl I need so that I convert that into grams. So I'm going to take 0.5 liters, that's how much I want to make, and I want to make 0.1 moles per liter. So that means, oops, why did I just write equals twice? So that means I need 0.05 moles of HCl. And then I want to multiply that by the molar mass of HCl to get this into grams. So H is 1.008 and Cl is 35.45. Oops, didn't line up the decimals, but that's okay. Doing this in my calculator because I don't want to mess it up. Okay, the molar mass is 36.458. 36.458, that's how much 1 mole of HCl weighs, and I only need 0.05 of a mole. So that is 1.8 grams of HCl. And then draw my procedure. So I would have a 500 milliliter volumetric flask, and I would add a little water, add 1.8 grams of HCl, swirl to dissolve, and then fill to 500 milliliter mark with water. And then I'll have a 0.1 molar solution of HCl. And I'll have 500 milliliters of it. But there's another way I could do this too, because it said that I already have a 12 molar stock solution. So I can use the formula M1 times V1 equals M2 times V2. M1 is the stock concentration. V1 is the mystery. I want to make 0.1 molar and I want to make 500 milliliters. So then I'm going to divide both sides by 12M to get V1 by itself. So I'm going to do 0.1 times 500 divided by 12, 4.2 milliliters of stock solution. So to draw a picture of this, here's my 500 milliliter volumetric flask. I'm going to use a graduated cylinder. Okay, and I'm going to make my stock solution blue. Okay, so this is my 2 milliliters of 12 molar HCl. Oops, my H is bad. I'm going to add that into my flask. Okay, so there's my, it's not very much. And then I'm going to fill to the line with water. Okay, this is water. And then overall, I'm not going to have a 12 molar solution, I'm going to have a 0.1 molar solution of HCl. Because that stock solution is going to be spread out. Okay, next. I can explain factors that affect kinetics, reaction rates. I can explain collision theory with regard to chemical reactions with varying concentrations of solutions. Okay, it says, imagine you have the following materials available: powdered zinc, big lumps of zinc, hydrochloric acid, 2 molar, a hot plate, an ice bath, a stopwatch. Which of the following questions could you investigate regarding the reaction between zinc and hydrochloric acid, which forms hydrogen gas and zinc chloride? What is the effect of decreased concentration of hydrochloric acid on reaction rate with zinc? You only have one concentration, so you'd have to do some work. You could do it, but you could definitely do decreasing temperature because you've got ice and a hot plate, so you could heat up some hydrochloric acid and cool it down. You don't have a catalyst. You could also do surface area because you have lumps of zinc and you have powdered zinc. So you could test each one in the 2 molar hydrochloric acid and see what the rate was. What effect would you expect to see on the reaction rate, assuming that you could perform all of these? So for letter A, if concentration of HCl decreases, the reaction rate with zinc would also decrease, because with a lower concentration, there are less solute particles per liter, and so this reactant solute doesn't collide as frequently with the zinc, leading to a slower reaction rate. What is the effect of decreasing temperature? If temperature of HCl decreases, the reaction rate with zinc would decrease, because with a lower temperature, the solute particles, the HCl, really H plus and Cl minus, because they dissolve into ions, move slower and are therefore less likely to collide with the zinc, causing a slower reaction rate. Right, if they're moving slower, then they're not going to collide as often. What's the effect of introducing a catalyst between the hydrochloric acid and the zinc? If a catalyst is introduced to this reaction, it lowers the activation energy necessary to break the bonds of the reactants so the reaction can take place. This results in a faster reaction rate. And last but not least, what's the effect of increased surface area of zinc on the reaction rate? If the surface area of zinc increases, then then there is a better chance that the zinc will come in contact with the HCl, therefore increasing the reaction rate. Okay, then we're on the last one. I can explain what's meant by chemical equilibrium and predict whether a change will cause the reaction to shift left or shift right. Well, if something's in equilibrium, that means the rate of the forward reaction and the reverse reaction are the same. So once you put a stress on the system, then the equilibrium will shift to try to decrease the stress. So for this first one, if you lower the temperature, that's going to cause this to shift to the left. Because it will try to compensate. So the CO and H2 will react more to try to make up for the lost heat. So the reverse reaction speeds up. If you increase the pressure, this will shift left. There are two gases on the right and only one on the left. So the product side is more affected by a change in pressure. So the reverse reaction speeds up. Removing removing H2. This will cause it to shift right. The forward reaction will speed up to try to make more H2 to make up for the loss. It's like, oh no, we're short on H2. And if you add H2, it's going to do just the opposite. It'll shift left. The reverse reaction will speed up to try to get rid of the excess H2. And the last one says, the diagram below represents a mixture of NO2 and N2O4 in a 1 liter container at 25 degrees Celsius. The two gases are in equilibrium according to this equation. I think that's supposed to represent a reversible arrow here. Which of the following must be true? Okay, so the equilibrium constant is the concentration of the product over the concentration of the reactants. So let's see what's going on here. There are more NO2s. Look, 1, 2, 3, 4, 5, 6. Then there are 1, 2, 3. Okay, so that's favoring this side. There's more of this. So what would that mean for the equilibrium constant if the bottom number is larger? That would mean a small between 0 and 1. So it's greater than 0 but less than 1. So it would be choice B. Because again, you're dividing by a larger number. This isn't the concentration, but if you did 3 divided by 6, that would be 0.5. So there you go. Hopefully that helps you out on the review.